We request all the participants to mute their audios.
സാറേ എനിക്കത് പറ്റുന്നില്ല. അത് കാരണം ഞാൻ കോളേജായിട്ട്
All the participants may please mute the audio.
Ibn, is it audible? Is it audible?
Yeah, I can hear you.
Yeah.
Can you hear
Good
me?
afternoon. Good afternoon. Yeah. So we have 5 minutes.
Okay.
Start. We'll start.
5 minutes will start. Welcome you all to this session. We will add this shortly, just 5 minutes. We will wait for.
Vipin sir, can you say it much more louder?
Sir, it is not audible. Please increase the volume.
Can you hear me?
Yeah, it's audible.
More participants are coming. We'll wait for another 5 minutes.
1 or 2 minutes. Yeah, 1 or 2 minutes. Right. Yeah.
Prince sir.
Yeah. Shall we start? Almost 3:30 it seems.
Good afternoon, one and all present here. Hoping that all of you are safe during this COVID pandemic. Stay safe. Always wear mask. Before starting, I kindly request all the participants to mute the audio till the end of the session. When you want to talk to the distinguished speaker, you can use the chat box. You were not able to attend the last session, which was on the opportunities in material science by Dr. Arun D.I., VSSC, ISRO. Its video is uploaded in our YouTube channel. Those who missed out, you can go through that. Once again, a warm welcome to all. As you all know, today we are having the second session of the national webinar series on prospects and career opportunities in metallurgical and material engineering, the way forward, conducted by the Department of Metallurgical and Material Engineering, College of Kalpakkam. Moment. I am very happy to you, Dr. Shaju Albert, Director, Metallurgy and Materials Group, IGCAR, Kalpakkam, Dr. John Felix Kumar, Head of the Department, and faculties, and professors, scholars, and everyone else present here. To start with, I would like to invite Dr. John Felix Kumar to deliver the welcome address and to introduce our distinguished speaker. Over to you, sir.
Good afternoon. As head of the Department of Metallurgical and Materials Engineering, Metallurgy College of Engineering, Kanjirapalli, Kerala, I welcome you all for the second webinar of National Webinar Series on Prospects and Career Opportunities in Metallurgical and Materials Engineering, the way forward, through this online platform. The National Webinar Series consists of 8 talks from eminent scientists and professors from reputed institutions and organizations on a weekly basis. The webinar series has been inaugurated on 11/7/20 by Reverend Dr. Matthew Poigar, Father Manager, Metallurgy College of Engineering, with the initial talk on a rendezvous with opportunities in material science by Dr. Arun, Scientist, Composite Materials Entity, ISRO, Trivandrum, and Dr. Chakravarti, Associate Professor, IST Trivandrum, with more than 150 enthusiastic participants. Today on this second webinar, I extend my warm welcome and special thanks to our resource person, Dr. Shaju K. Albert, Director, Metallurgy and Materials Group, Indira Gandhi Center for Atomic Research, Kalpakkam. Dr. Shaju K. Albert has authored many research articles with more citations and guided more research students. The topic of today's webinar is properties that cannot be predicted from the periodic table. In celebration of the periodic table's 150th anniversary, the United Nations declared the year 2019 as the International Year of the Periodic Table, celebrating one of the most significant achievements in science, commemorating Russian chemistry professor Dmitry Mendeleev and German chemist Julius Lothermeyer, who independently published their periodic tables in 1869 and 1870, respectively. The various different forms of periodic table have stimulated the question of whether is there a complete form of periodic table. And the answer to this question is supposed to depend on whether such periodicity is instead the product of human interpretation, dependent upon circumstances, principles, and preferences of human observers. With this, I invite Dr. Shaju K. Albert to deliver the lecture on properties that cannot be predicted from the periodic table. Welcome, sir.
Thank you so much, and thank you for giving me this opportunity to speak on your webinar. And I special thanks to Manu and his colleagues for enabling it, and also to Mr. Savesaji, who was my student and who made me agree to this. And I hope I would gist this, and professor has already given a nice introduction about the periodic table. In fact, the talk I am going to present now is only an extension of a talk which I gave when periodic table centenary was celebrated in the UGC center in IGCAR. So as I was told, this webinar is focused for the students of no, +2 students who have completed and who's looking for a professional opportunity. I thought I will not go to more and more detail about our research work, but confine ourselves as much as possible on topic which they already know. And in that moment, through that route, I will try to generate some interest in the young minds about the fascinating field of material science. So, are you are able to hear me?
Yes, sir. Yes.
It's okay. Audio is okay.
Sir, we can hear you.
Okay. So I'll continue with this.
Yes, sir. It's fine, sir.
Sure, sir.
Okay. Okay. So as I told, the property that cannot be predicted. Now, when you may be wondering what are the properties that cannot be predicted. So we are not going to talk about any property about which we do not know. In fact, we are going to talk about the properties which we know we encounter in day-to-day life. Okay. So shall we go to the next slide? No. So a brief word about myself. So, see, at present, don't think that I am beating my drum, but just want an introduction purpose. So, I am my material science group and metallurgy group in IGCAR Kalpakkam. I am also senior professor in the and board of studies member in the Homi Baba National Institute. And professionally, I am also chairman of committee on welding, because that is my specialization on Bureau of Indian Standard. I also served as a vice chair president of Indian Institute of Welding and also chairman technical committee and Chennai branch of Indian Institute of Welding. So I am also have a privilege to be associate director of Welding in the World and International Institute of Welding official journal, and I have also have other responsibilities. So I graduated in metallurgy from Indian Institute of Science, Bangalore, 1984, and I had a PhD from Indian Institute of Technology, Bombay, 1997, and I was also a fellow and worked in National Institute of Material Science in Japan. My area of research is welding metallurgy and then about nuclear materials. And so now I want to, why I put this information on the slide, I just want to tell you when I was a +2 student or equal to +2 student in my time, it is a pre-degree. I was just an ordinary boy, and I was the son of a central government employee and a high school teacher, and had my primary education in Malayalam medium in a convent school. Then went to a government school for my higher studies and had no plans to become an engineer. I went to study BA after my +2, and my only exposure to Department of Atomic Energy is a long distance view from Arabian Sea when I went on LTC to Bombay. So could not have spoken or written a few sentences without making many mistakes. This is my thing. That is in English. That was my status when I came. So I'm just telling you this because all young minds, they need not be worried about any negative feeling about what they are now, but they can achieve things if they work hard and they have more and more opportunity. So next slide, please. So periodic table. As I already, I think Professor has already explained the beginning of the periodic table. He also mentioned both the names of Lothar Meyer and Mendeleev. So I dedicate this lecture to both these people who made a tremendous invention or organizing this. And I just read an article in American Scientist. So there it mentioned this is probably one of the best organized information in any scientific field. So next slide, please. So we now we know the periodic table as it is today. So I just want you to look at the arrows which I have marked in different vehicles. So there's an arrow against. We all know there is periodic table is divided into groups, and the group elements in following one group they are supposed to have similar properties, that we all take it for granted. So we have and we study the first group is of alkali metal groups, and there we have sodium, potassium, all elements. And there in the seventh group we have alkali halide metals and elements. And what interesting thing we want to note about it, the periodic table we find is most of the elements we have are in the periodic table are metals, 80-85% of them. And if you remove the inert gases, we have very few gases, 3 or 4 gases only are there. And I also want you to note down there are only two elements which are in liquid form at ambient temperature. One is a metal, another one is bromine. So these are all very interesting facts. And the arrows I have marked is with respect to the elements about which I am going to speak now. So as I told you, there is hydrogen, there is iron, there is aluminium, and there is carbon, silicon, oxygen, and then down to there is uranium. And there are many more. We'll come to those elements also, but this is just for the introduction. And next slide, please. So now, if you look at the major element that influence our human existence and progress, you'll find among the lot of elements present in the periodic table, we encounter or we use only very few elements. See, oxygen is meant for sustaining life, and hydrogen, okay, water, food, energy also come from hydrogen. Carbon, food and energy. You know how important is carbon, biochemistry, petrochemicals, everywhere carbon is there. And all other elements that I listed down, all metals, copper, iron, aluminium, titanium, nickel, all are meant for industrialization. So meant for, we make structural materials, we make bridges, we make ships, we make aeroplanes, all those things we use this material. And now what we have is silicon, then electronic revolution. This is and we also have a nuclear fission coming up, and that way source of uranium is also source of energy. And if everything goes well, soon hydrogen also may become source of energy. And the next slide, please. So now, if you look at over the centuries, this human anatomy or our intelligence, our physical nature has not changed much. But only thing is the way we dress, the way we our technologies have changed over several years. And as you know, progress, you will find that technological changes are faster and faster in the recent past. So we have earlier Homo sapiens, they used to hunt and live. Then it became started, agriculture started. Then the weapon industry started. Now we have modern technology coming up. Next slide, please. So in this, so how this happened? If you look at it, all these civilizational changes has happened with the development of materials. So some tools, we replace the stone as a tool with the copper materials, which led to agriculture, primitive agriculture. Then we started using iron. Then we have industry, weaponry, all this thing with iron-based alloys it came. Then now with the modern technology, we have a silicon age, but here still iron or metals ruled to large extent. We had a thing of plastic coming up in a big way, but now we know we cannot afford to embrace plastic as the way we thought. So we may still go back to other natural materials or metals for sustenance. So we go to the next slide, please. So now more important thing is why we use metals. See, if you look at it, the evolution from stone to copper or bronze. See, stone is much harder than copper, but still people left stone and started using metals. The main advantage of metal is it can be made sharpened, it can be formed into the shape and to the shape and dimensions which is not possible to do with the stone. So that actually makes it more useful than stone. Then what is the special property about the metal? So we have given in the center, if you look at it, there is a diagram is given, a graph is given with the strain versus stress. So if you are a +2 students, you might have done some Young's modulus calculation experiments in your physics lab. So what we get, we increase the stress and we increase the load and we increase the elongation change in dimension and we plot this. It's same as this. Now, when we have 3 lines, one with a very less slope, and that materials correspond to a soft material, and we have a one with a very sharp slope, strong and tough material, strong material, and we have the middle line. We have strong and tough. Now, what do you mean by strong and tough? So now we can for an approximation, a rock can be considered as a very strong, but and a ball, that ping pong ball, which is kept in the right side on the slide. This is can be a resilient, it's a soft material. While we have shown that pictorially a tough material, that is, he's taking a lot of abuse, still he's remain sustaining. He's not getting damaged. That Y shape which is shown there, so that we can pictorially show. That means it is able to, it is resistant both to metal as well as to it is able to withstand strong. It is not breaking. It is able to withstand load. So next slide, please. So now, why when you come to metals, one important thing about metal is alloying. That is, we do a lot of things because metals get alloyed. Pure metals not always very useful unless it is alloyed. Now let us look at what happened in the history. The copper initially people found the copper because they found the copper earlier than iron. The only reason is we could achieve temperature required to produce copper from its copper ore by burning fuel what is available. That is burning wood and other fuel which is available naturally. It was possible to get. That is why we found copper first. So copper, then we got bronze. Why we went to bronze? You can look at the slide. You can see bronze age was much longer than copper age. The reason is bronze has a lot of advantages. You can see the strength graphs shown here there in the bar chart. So strength of bronze is much higher than that of copper. And what is important is melting point of bronze is much lower. So that means to make bronze is much easier than to make copper. So it is stronger, it is easy to make, easy to melt. That is why bronze age lasted for a long time. Okay, next slide, please. So nowadays, in the present scenario, we don't use copper and alloys much as a structural material. We use it for a thermal conductivity, electrical conductivity still use, but not as a structural material, not for making knife, not by making hammer, not by making buildings. But for that is taken over now by steel and versatile in wide range of temperature and environment. And we use, for many applications, we use aluminum alloys. We find the titanium alloys increasing use because of oxidation resistance and lightweight. We also find nickel alloys for high temperature. And there are so many specific applications, specific alloys are there. So what I want to convey is the material has changed. Now, the most widely used among them is steel. Now the question is, why steel? Next slide, please. See, steel, all of you know, iron is the element and steel is an alloy of iron and carbon. So when you say carbon, alloy called iron and carbon, we may think that carbon content, for those who are not familiar with the metallurgy, they may think that carbon content may be the few percentage. No, it is only very less than 1%, maybe 0.1, 0.2, 0.3 like this. But addition of such a small quantity of carbon into iron make lot of difference. So I have shown you 3 figures. one is a stitching needle, and another one is orthodontic wires. For you, if you want to conceive the difficulty in conceiving orthodontic wire, you can just think about the wire which we get along with our modern bread package, tying wire. So then you can have a safety pin. Now you see that all the three wires are the needle, orthodontic wire, or the fencing wire, or the our modern bread twisting wire, and the dimension of the safety pin, the diameter of the safety pin wire, all are almost same, but their properties are so vastly different. So vast means you cannot bend the needle, but you can any number of time you can change the orthodontic wire or the fencing wire. But need you can have thousands of operation on the safety pin by removing it and putting it, locking it and unlocking it. Still, it will remain the shape. So three different properties. One is very hard, one is very soft, one is very tough. And if you analyze chemical analysis of all these three wires, for a person who is not familiar with metallurgy, he will not find any difference, because he will find that it may all contain some. The only difference, if you carefully look at it, the only difference may be some amount of the carbon level. And as I told you, carbon level will be less than 1%. So if you look at our own day-to-day life, the milk which we get contain several percentage of water, and we are not able to differentiate them. But in steel, you addition of few sub percentage of more than less than 1% of carbon makes so much of difference, and that is what makes steel so interesting. And I also want to bring it to here the interesting part about the steel. You know, steel, iron is magnetic material, but except for our electrical application, magnetic application, we don't, as a structural material, we don't use the magnetic property of iron much, isn't it? Most of our store well we use, it's not because it's magnetic. Our vehicles are made of steel, not because it is magnetic. But still, one point I want you to keep in mind: iron is magnetic. Okay. So you go to the next slide, please. So when you come to iron, see, India also has something to be proud of. See, in the different parts of the world, when iron was being produced or smelted or produced from iron ore, that is hammerite and other iron ores, India also had such techniques, and the tribals we had a technology from the among the tribals to make from iron ore how to get iron. And the wood steel, the legendary wood steel, which is used in Arabian the kings, they had that steel has originated from India. So that is Kuku steel also it is called. And more interestingly, this iron pillar which we have it in Delhi, it is also made of iron. It is 500 years old, and that time it was not possible to melt iron by the heat we can produce. So it is actually reduced the solid state reduction. That is, iron ore is reduced to solid state iron, and then iron powder is forged together to make this iron pillar. So we also had indigenous technology in dealing with iron. Okay, now next slide, please. So I think we need to spend little more time here, because the entire thing why iron is so useful is come from this. So now our thing is, we all know that matter exists in three states of matter, that is liquid, solid, and vapor or gas. So generally we have a low temperature, it is solid, and medium temperature it is liquid, and high temperature is gas. So we tell that the states of matter. But what is important is in the solid state itself, in the solid states, atoms are arranged in a definite pattern. That is why we solid state. In fact, they call as a crystal structure arranged in a definite pattern. So there also in the solid also we can have different forms, same element but arranged in a different order can produce different crystal structure. And we all studied this in even our +2 or even a high school. we call them allotropes. We have studied about allotropes of sulfur. We know the famous story of carbon and diamond. They are all allotropes of carbon only. So similarly, in the case of steel also, iron also, there is a two allotropes. There one crystal structure of the one allotrope is BCC. That is what is given in the bottom. BCC means body-centered cubic. So we have a cube there. The corner we have in the dark circles atom, and in the center of the cube also we have atom. So this is called a body-centered cubic. And when you go to high temperature, this body-centered cubic structure changes into another structure called a face-centered cubic, and that picture is also shown. So here we have, instead of atom in the center of the cube, we have an atom sitting on every corner, every face, the face of the cube. So that means we can roughly find out we have more atoms in per unit cube in FCC structure than in BCC structure. Iron at room temperature is BCC. It is called ferrite. And what you call at high temperature, normally iron is oxide, called FCC. If you want to define what these two are, in our home, all the steel plates in which you take food, they are basically, most of them are austenitic stainless steel. That is, there they are, by adding more alloying elements, they made a FCC structure stable even at room temperature. But our window frames and our vehicles, automobile vehicle, all are made of ferritic steel. That is their BCC structure. Now, 2 points I want to convey here is, see, this is called the FCC structure is called closed packed structure because more atoms are there. The space, empty space is less. This structure is closed packed. While BCC structure is open because less atoms are there per unit cell, so it is called open structure. Now, if you look at, if you have put a vertical arrow of temperature, you can see that means at high temperature it become closed packed. At low temperature it is become less close packed. That is open structure. But this is against our normal law because we know metal expands when you heat. Not only metal, any solid expands when you heat. We know atoms vibrate faster and faster, and their atomic distances increases. That is why it expands. Now that means thermodynamically, an open structure should be stable at a high temperature, while a closed structure should be stable, if possible, should be stable at low temperature. So apparently, this is not happening here. We have surprisingly, we have a open structure at a low temperature and a closed structure at a high temperature. And this is one aspect. Another interesting aspect is when we add iron, carbon into iron, the carbon will dissolve into iron. That is what we are saying. So now the thing is, solubility of carbon in iron, in BCC structure is very less. Though it is open, actually carbon will go. How carbon dissolve in iron is actually it will sit into the gap between the atoms. You can see the gap between two atoms, but it will be there. It will go and sit there. It is called interstitial site. It will occupy. That is how carbon dissolve in iron. But now what happened? Soluble size of the interstitial in BCC is much smaller than size of the gap which is available in FCC. Then you may naturally wonder why it is so. Because you said, I only just now said that is close packed, then how the size can be bigger? So I will just take you an example for you to explain this, because I will not go to the details of metallurgy here, but just a simple example. We assume a bench, one bench in a circular form and another bench in a straight form, and with three people are sitting. So between the two, when you have a straight bench, we will have two gaps between the three people. While when you have a bench in a circular form, we will have three gaps between the three people. That means number of gaps are more, but in the circular bench, but the number of gaps are less in a straight bench. But since number of gaps are less in a straight bench, the gap between the bench will be larger. So similar way only it is. We will not go beyond. What we have to take it is, we have more carbon can dissolve in FCC structure, that is austenite, but less carbon only can dissolve in BCC structure. Now the entire steel metallurgy is based on these two principles. Now the thing is, so that is what I written here. See, what makes iron carbon system so versatile? Transformation of open BCC structure to closed FCC structure at high temperature. If this transformation is not there, suppose it was only throughout the melting, it was only BCC or FCC, then no significant change in carbon solubility. It will not change. It's not changing. It will not. I will not get. Once you more carbon is FCC structure, with the more carbon is cooled down to BCC structure, which can take less carbon. Then only steel become hard. So if it is not there, it will not become hard. Then if the once it is hard, we can have an option to reduce the hardness by doing again one heat treatment. So we can heat it to high temperature the way we want, and we can have different strength level and toughness level, softness level the way we want. All those things are possible because this transformation. Not only that, the BCC structure. See, we all know how blacksmith does. See, you have seen if you go to a blacksmith to make a hammer. So what he will do, he will put his iron piece in the furnace which he has made. Then he keep it for some time. He blow air so that temperature will go up. And finally, when he feels that he has so much experience by looking at the iron piece in the furnace, he can determine what is the temperature. So and depending on that, if you want to make it hard, he will punch. But you have to punch. That's what we told. That I told you we can make. But if you want to form, change the shape, he will not punch. He will take it from this and he will hammer. When the temperature goes down, it becomes difficult to hammer. He will put it back again. That is what I told you. He can be formed easily when structure is in FCC. So at high temperature is very good, easy to form because structure is FCC. And we can quench and we can change the property. All those things can be used. Now, if it is not there, then iron would not have been useful at all. The entire use of iron, the steel, is based on this principle. So now you find this material, iron, have a special property, which because of which it is still continue as a major structural material in the human civilization. Now the question is, why this anomaly? That is, why an open structure is stable at high temperature? Is stable at low temperature, and a closed structure is stable at a high temperature. And this is here we will be more interesting thing. I can go to the next slide. Next slide once more. So no, go back. So here I do not know how much a +2 student can appreciate, but we all studied specific heat of metals and elements. Specific heat, what does it mean? Specific heat means that heat required to raise the temperature by 1 degree for 1 mole of metals or 1 mole of compound. That is one. So now here what happens is, you can see the left side diagram. So what is the specific heat variation is influenced by the properties, magnetic property of the FCC structure and BCC structure. Now I can just show you. We'll go to the right side. Right side, what is written text? First written text. That is, you see anti-ferromagnetic to see FCC structure is anti-ferromagnetic. We know iron. We call iron as a ferromagnetic. When we say iron as ferromagnetic, what we mean is BCC iron. Ferrite is a ferromagnetic. But austenite, which is stable at high temperature, it is anti-ferromagnetic. You know what you mean by ferromagnetic? Ferromagnetic means all magnetic domains are aligned in the same direction. That means anti-ferromagnetic is they are aligned in the opposite direction. So now that we call is paramagnetic. That is what most of the elements are. Most of the metals are paramagnetic. Their magnetic domains are randomly oriented. So now what happens is, the austenite, which is anti-ferromagnetic, become paramagnetic at 1 temperature. Similarly, ferromagnetic ferrite, which is ferromagnetic, become paramagnetic at a higher temperature. Because of this, so there is a specific heat, there is a contribution from the magnetism coming into iron because of this behavior of austenite and ferrite. Now, because of this, you can see at low temperature in the left side graph, you can see in the left side graph at lower temperature, we can see that austenite is at a higher, the specific heat of austenite is higher, and specific heat of ferrite is lower at low temperature. But this is because you can see a peak at low temperature for austenite, the dotted line. You can see a peak in the graph towards the left side. So that peak, because of this peak, that curve shape is changing. Similarly, when you go to high temperature, similar transformation of ferromagnetism to paramagnetism, there is a peak for ferrite. Because of this shape or this specific heat variation, you can do the middle graph. You can see that the free energy. I don't know how much you will understand free energy, but free energy is a energy which will determine which phase is stable at one given temperature. So we can see free energy curve for both austenite and ferrite, or what we call alpha and gamma. They are crossing each other, and it so happens that at low temperature we will find ferrite phase is stable because it has low energy. At high temperature, austenite phase is stable because it has a low energy. And when you go still higher temperature, above 1000 degrees centigrade, then we find again ferrite phase is stable. So this is coming because of magnetism present in the steel. Now you look at this entire application of metallurgy of iron is coming because iron is magnetic. Suppose you imagine a situation iron is not magnetic, then much of the use as an iron as an engineering material would not have been there. So this is what I am saying when we say that this we cannot take from periodic table. Periodic table, as per the periodic table principle, we should be able to the adjusted element which is next to iron, below or left or right, should have a property similar to that of iron. But this property is not there because the next element next to iron is cobalt, or next below before iron is manganese. They cannot replace iron for this property. So this is what I said, these properties of the, and now the entire civilization, human civilization take on this property of this iron of this. So this is what I say, the properties which we do not, we are not able to directly predict. If you go deeper into chemistry, we may be able to predict. We are able to predict. But from the periodic table, that is not obvious. So this is what one property, and that is what sustain our life. So now we'll go to another interesting material. Next slide. I want you to think how many we know. We told already 80% of the 80 or more than 80 elements are metals, and we know all of them are white in color. It's in bright white in color. But there are only two elements, two metals which are of different color, and they are copper and gold. Can you imagine if gold was like a silver or like an iron? How many jewelries would have been there in the world using gold ornaments? We know platinum is also be considered as a rare metals, but people still don't use the platinum jewelry. People still use the gold jewelry only. See now, if gold is not having white, having a yellow color. Now it is interesting to know why gold is having a yellow color. And similarly, copper is having the color, it has something like a red color. So now it is interesting thing to know. We all know why metallic luster, the principle of metallic luster is metal is able to reflect the light. So that is why we say why metal is able to reflect. So if the white light falls, in all other metals, white light is reflected, but only in copper and gold, white light is not reflected, and the color we get is only red color in copper and yellow color in gold, but in silver and other metals we still get this. The science is because we know in the metallic structure there is a free electrons. This electronic shell. These the electrons are free. Of the atomic electrons, the outer shells are free in the case of metals. We will not go deep into it. And on the surface of the metal surface, these free electrons, they don't have any neighboring, the surface is free. As a result, what we call them as a plasmons. The electrons which float around on the metallic surface is called plasmons. When the light falls on them, they take the energy from light and they get excited. And but depending on the excitation, only this comes. Now we have a graph here which shows. See, we know one thing. Light is an electromagnetic wave. Starting from hello. Are you able to hear me?
Yes, sir. Yes, sir. No problem.
No problem. We have a spectrum coming from one end of the wavelength to the other end. So we have an infrared, ultraviolet, which is beyond the light range. So now, in the case of elements, gold and the copper, the outer shell electrons, that is especially, electrons are arranged in sp-df orbitals. So in the outer shell, s electron orbitals and p electron orbitals are such that they absorb, they have a tendency to absorb visible light, while all other metals, they absorb either in ultraviolet light or infrared light. That is what you have shown. See, you can in the graph you can see here for gold and silver. See, this is a 100% light. See, this is for aluminium, this green line. So you see, it is not absorbing any light, 100% reflected. Only in infrared it is absorbing some energy. This is for silver. This light, there is a silver line. You can see it is absorbing at and in the ultraviolet regime. And when it comes to visible light regime, it is not absorbing, it is reflecting. While in the case of gold and copper, it is absorbing light in visible range. So as a result, copper absorb blue light and it reflects only the rest of the light, so it looks red. Gold absorb gold absorb red photon and it become yellow. The rest of the color is yellow. This is how it is. So now you imagine if this is the case, how gold and copper would have been useful. At least copper has other application. Gold would have been almost a useless material. So this is one property which we don't get from our this. So this is, I think, can you go to the next slide? So this is actually, we'll not spend much time here, but I just gave you that the electronic arrangement, how the in a transition metals, how the electron shells are getting filled and how this energy comes. So what is happening is, why this particular phenomena happening is because when large atoms, when the nucleus size is the number of protons become larger and larger, number of protons increases in the nucleus, its effect on attracting electrons from the outer shells become more and more. So now when you have electrons which is with one electron and s level or two electrons s level, they have a tendency, the two electrons in the s level and so much of new protons in the nucleus. So force exerted by the electron as on the s shells of electrons will be high. As a result, s shell radius will come down. They become closer to nucleus. Then now they are spinning around the nucleus. We know their velocity become more and more. And as a result, the other electrons, the transition from that shell, will not go finer details, but transition from that shell, from S shell to the remaining SP level or D level become easier. As that is how this absorption and desorption take place. Now we find it is a favorably placed only for these two elements to be in the optical light range. of all other elements, it is either in the ultraviolet range, as in the case of silver, or in the case of infrared range, as in the case of aluminum. This is how it is. This. And now you will find another interesting thing. I told you there is only one metal which is liquid. You can go next slide. Now, before going to the liquid metal, this is also an interesting aspect here. See, now we have also very interesting part of gold nanoparticles. See, whenever people talk about nanoscience here, everybody will be knowing. So, when you have nanoparticles, what is the first principle of a nanoparticle is particle size is so small. That means you have a large surface area, because all particle size is more surface area. So surface then against the plasmon, that what we call the outer electrons on the surface become more, and this property can use different colors. So that is why you can have a gold coated the cups can have a different color depending on the size and distribution of the nanoparticle. So this also we can get. Again, because interesting science. Now you see almost the same reason. For the same reason is why mercury is liquid. Now what is happening? The reason is what I told is the same. That is mercury is a heavy metal. So it has large number of protons. So the attraction of the nucleus on the especially electrons in the s band is very high. So they come back, they come closer to it, their velocity increases. As a result, there we told light absorption. Here what happens is atom to atom interaction become less because of this special feature of mercury. That is the atom to atom bonding become less. So as a result, see when you say liquid, atoms are atom to atom or molecule to molecule are able to slide down, it become liquid. So otherwise, if they are bonded together, then they become solid. So here, because of special nature in mercury, it become the atom to atom force between atomic bonds are weak. As a result, mercury is liquid at room temperature. It will be interesting to note in the periodic table, mercury is next to gold. You see mercury and gold, and both are very dense metal, but their properties are so vast. So they are next in the periodic table. So this is what another thing what I am to your notice. The things which we know, we may not be thinking about it, but we know very interesting. So even though we are next to the periodic table, their properties are so vastly different, all because of finer details of atomic electronic in the atom. So this is what I want to convey. So we'll go to the next slide. So this is nowadays. This is a very interesting aspect I want to just bring to your attention. See, you know, nickel nowadays we use widely for very specific application. But nickel is very close to copper in the periodic table, and their chemical properties are also similar. So when olden days, when people want to make copper, they used to come across nickel ore also, and the nickel ore will not produce copper, and they had so much of desperation while making copper, and they believed some evil spirit is mixing with the copper ore, and that is why they are not getting proper copper when they melt. And they the word nick comes from evil spirit, and then only that is how the element nickel is named as nickel. So that is in olden days, in a few centuries back, nickel was a useless metal, and it was a curse to have it. But today things have changed. Nickel is a much sought after metal, and only thing properties which you use, it is actually for a different reason, for the high temperature oxidation resistance application. Can you have the next slide? See, nickel based alloys, because of their specific arrangement of the atoms, it can have very special properties. They are called ordered structure. The middle structure is shown. What is an ordered structure will look like? An atomic arrangement ordered structure is shown in the left figure. So now this ordered structure improves the property so much, and then nickel alloys are called as super alloys. Actually, they are superman in the alloy system. So now you see an element which was considered as a curse in the past now become a Superman in the present. So this is again an interesting aspect which we don't get from our periodic table. So now go to the next slide, please. So now we come to the most interesting element of the universe. See, carbon. So you see, we have just put some photographs. See, we have charcoal, a charcoal soap where dust is there. That is also carbon. Then our pencils are also carbon. And the bottom you have a diamond. It is also carbon. Then you have and which is meant for as an ornament. While we have a diamond used as an industrial cutting tool, we also have. And we have the right side. You see that graphite is and graphite and charcoal are so soft you can use them to draw a picture as you shown there in the right side top. And it is a diamond is so hard you can just by making a line on a glass you can cut. So vastly different properties, but same element. As far as the chemistry is concerned, both are C612. So now it is a carbon is an element. Now it is not only with respect to elemental form, it is interesting. You can go to the next slide. It is not only with respect to the element form, it is important. You know, the entire organic chemistry is based on carbon-based material. It can form very, very interesting compounds. In compounds which we cannot think of. It can form I don't want to spend more time here. So which but we all of us know organic chemistry based on carbon. We know benzene is one form. We know the methane, ethanol, all are is another form. And we have a by changing the hydrogen in the methane and not we can for other forms. All those things come from carbon. And it is there in a biological material. It have in the fuel. It is there in the food. It is there in our cell. In the food we take, it is there in the fuel we burn. Everywhere carbon is there. Okay, it is also accompanied by hydrogen. So, but this is but you see it even in our in without any difficulty at room temperature itself, it is available in different forms. And now, next slide, please. So we have all these different forms of carbon. See, these are just an example of how, as a coal, as a graphite, as a diamond, as wood, as a hydrocarbon, as a biogas, as LPG gas, everywhere carbon is there. So all those are fundamental law life chemistry. So now we go to the next slide. So now carbon itself, as I told you, it's only a C612, that is 6 electrons and 6 protons and 6 neutrons. That is what it is. But it can be arranged in the form of a diamond. It can be arranged in the it's a crystal, solid crystal structure, and it can be arranged in the form of a graphite in a layered structure. Now we have other allotropes like what we call fullerenes, carbon nanotube. Lot of interest is there. Many thousands of PhDs are being produced nowadays on material properties of carbon nanotube. Carbon nanotube, different forms, and carbon nano sheets. Carbon sheet is there. Carbon paper is there. All those, these are all in small quantities, but they are interesting. Lot of interesting properties are coming. So a metal which is there in the so much an element which is there in so many different forms, so much of application. Next slide, please. So see now what is graphite is tightly bonded carbon atom are set out in a loosely bonded layers. So one layer is strongly bonded, but they are connected by a loosely bonded layer. That is why it is able to slide, it is able to draw pencil, we have to make a pencil, everything. And diamond, but by strongly bonded directional bonding, we cannot change. Now we have another thing, graphene, which has come. That is carbon nanotube and graphene single layer of carbon atom arranged in a hexagonal mesh and then lattice. Graphene has a tensile strength and it has a strength much higher than that of steel. And so this is a very unique material. We cannot make in large quantities, but it can be formed in thin layers, and many layers can be made, and that way you can make it bulk. And all those things are going on. And we have a Fullerene structure, which is in the case of a in the form of a football. Structure is like a football. I think you can go to the previous slide. Can you just go to the previous slide? previous. So the fullerene structure is there, and this is the graphene structure where hexagonal layer is there. So all this structure is all because of the new things about carbon. So such a versatile material. We can go to the next slide. So we'll go to the next slide now. Now you see just for a much more clarification of the structure of diamond and graphite. So the crystal structure are different, also the properties are different. And you will also, I do not know how many of you know that the diamond, which is so hard and very strong and which is very resistant to all forms of corrosion, actually they will not last beyond 300, 400 degrees centigrade, because carbon, diamond form of allotrope of carbon is not a thermodynamically stable phase. So if you heat it, it will turn back into graphite. So everything is fine. A diamond is strong, but if you can be very strong, the strongest naturally occurring form of element but if you go to a heating furnace, it will simply become graphite. So that bonds will break and go to the next thing. But nevertheless, it has got an opportunity. This one. See, now if you come to the chemistry form of it, we already know why carbon is so interesting in the not only in the form of elemental form, it is also interesting in the form of chemistry as a compound form. So you can have a straight bond, branched bond, ring bond, so many, and depending on the compounds can be different. And we can have a long compound, large compound, small compound. We can have things in the gas form. We can have things in the liquid form. We can have things in the solid form. We can have things in the thermosetting form. We can have things in the thermoelastic form. All those things is possible, all because of special property of this. Now my question is, next slide please. See, all those things forms are possible. Now question is, the just below in the periodic table is carbon is silicon, but we don't have a silicon chemistry like carbon chemistry. But we use silicon for a totally different application because it's semiconductor properties. So do you think that this is again is a very interesting thing? So we have a periodic table, we arrange metals in the way most chemical properties, but the properties which we are interested in, they are unique for both these metals, even though they are the same periodic in the same group of periodic table. That is what I want to convey to you. Next slide, please. So we just want a story. We literally live it and breathe carbon. It feeds our industries, inspires our labs, and is the cause of potential solution to some of the greatest challenges facing the planet. Carbon is so ubiquitous across living organism that radioactive in measurement. See, carbon dating is used because carbon is there in every product or every form of substance. So carbon dating can be done. So it is so important. So periodic table, this but periodic table does not say carbon has all these unique properties. Go to the next slide, please. Sorry. Now let us look at the compounds other than elements of carbon. We talked about mainly about elements other than carbon. Now let us look at some compounds. See, we also use many compounds in our day-to-day life. We have lime, brick, cement, alumina, magnesia, silicon dioxide, carbide cutting tools, glasses, everything, many different compounds. I just want you to guess what is the most widely used oxide by mankind. You can just guess it. I will wait for you to guess for a few seconds. See, since it's not interactive, we cannot get the answer to you, and I don't want to.
Silica.
Anybody unmute?
Silica oxide. Silica, carbon dioxide.
Yes. Okay. Anyway, you have told some answer. You go to the next slide. See, I am sure many of you. See, you already nobody told the right answer, but I am sure many of you would not have guessed it right, because we take the most widely used compound in our day-to-day life taken for granted. It is water. What I told is oxide, most widely used oxide. It is hydrogen oxide. Is it correct? H2O. And you look at some more surprises. See, can you guess any other oxide which is in liquid form? You will not be able to guess. I put in an internet oxides in the liquid form. The only oxide which is available as to us in the liquid form. When I searched the internet and for an oxide, it is told chlorine oxide, chlorine with the 7 with the valence 7 oxide, a compound and which you and me have never heard of, and it did not say water. So see, now both oxygen and hydrogen are gases, but you see, hydrogen is a oxide is a hydrogen dioxide is a liquid. This is not the case with the nitrogen and other gas which also form oxide. Oxides of nitrogen is not liquid; it is a gas. Now you see oxides of other non-metals. Your carbon dioxide is not a liquid. Liquid. It is a gas. So, but if you look at silica, silicon dioxide is a solid. And if you consider now, if you consider the position of hydrogen in the periodic table, it is along with alkali metals, on top of alkali metals. And if you consider hydrogen as a metal base on its position in periodic table, then it should have been nitrogen oxide. Hydrogen oxide should have been solid, like NO2O. It is not that also. It is just liquid. Now we know it is a hydrogen bonding. Now we know it is because of hydrogen bonding it is. Now you imagine a situation how our life would have been if hydrogen oxide or water as a gas, or it was also as a solid. But it is not. And can you guess it from periodic table? I am sure you will guess it. Okay. So now can you go to the next slide? So this is what my summary is. I am stopping at it. So periodic tables do not provide does provide a very useful presentation of elements with respect to their mass number, electronic structure, chemical properties. However, it's a unique property not often revealed from their position periodic table that we have made life to exist as we experience it today. Our life exists today because of unique properties which we did. And what do we mean by metallurgical study? Study of these unique properties of different materials in solid state. Okay, gas we cannot say metallurgy or material science. Is a be it metals, non-metals, semiconductor, or inorganic, organic, which make the material science an interesting subject. So I conclude, I am proud of being a metallurgist. Thank you so much. So you can maybe you can put questions in the chat and we can answer.
Thank you, Shaju sir, for the very informative and inspiring talk on the world of materials. Dear participants, now the session is open for questions. You can ask questions through the chat box.
Maybe somebody can combine and then ask the question to me, then I can answer.
Will help, will help.
Sir, many participants are asking some questions and many are still, many questions are coming up in the chat box.
Yes, yes.
I'll just summarize for the benefit of the participants. Some of them are technical questions, and what is the other oxide in liquid than water present abundantly?
No, nothing is
asking, what is the other oxide in liquid than water present abundantly?
I think nothing is present abundantly. What I saw in the internet is chlorine and with a valency of 7 and forming a compound with oxygen. It is in liquid form, but I don't think it is a you have to produce it. It's not available on its own anywhere.
If the participants have any other queries, please post them in the chat box so that we can have a discussion now.
Sir, another question. So why does the heat capacity of iron change abruptly during transformation of paramagnetic to ferromagnetic?
See, whenever there is a change in the state, see, like it is very simple. But you know latent heat of fusion. We know about water. See, because it's changing from solid to ice salt. There is a latent heat of vaporization is there. There is a phase change. Here there is a crystal structure change or matter state of matter change. There is a heat change is required. Similar way, when the material is changing from a ferromantic state to paramantic state, there is a heat, some energy is required, and that change is reflected in the heat capacity. Exactly the same by latent heat of fuel and latent heat of vaporization.
So there is another general question coming up. Can you give a little idea of how metallurgy is of importance in atomic energy plants? What does metallurgists do there?
Metallurgy has two important aspects in the atomic plant. The most important thing is fuel, that is nuclear fuel. See, it is uranium oxide or plutonium oxide or uranium metal or plutonium metal or things. So extraction of fuel in the water. See, we have iron, like iron ore, we have uranium ore. From there, we have to bring it to either in the form of a uranium oxide or uranium metal. This extraction of metals and production of this is itself is a big challenge, and we have to make them in the desired product form to put in the reactor. This is the major part of work which metallurgists, one part of the work which metallurgists do. And another thing is there is a very important aspect of materials under irradiation, material property change. And not only that, many metals absorb neutron. See, if neutrons are absorbed, see, the fuel, even though we cannot put the fuel just like that in a reactor, it has to be contained in a form of a tube or plate or something. It will be contained in the form. So that means it has to be covered with some steel, some metals, a structural material. It has to be contained in the structural material, tube form or plate form or whatever it is. And that containing material, if it absorb a neutron, then this most of the neutron goes to absorbed by this structural material, and we will not have sufficient neutron for nuclear reaction to continue. So similarly, not only that, these neutrons will change the property of the materials. Actually, it will make a material brittle. It will be all the more dangerous. So another important aspect metallurgists need to study very extensively in atomic energy is that the behavior of material under nuclear irradiation. That is a very, very important part of the study. In the next, we need to do structural material. That is the material, the pressure vessel we have to fabricate, heat conducting pipe system we have to fabricate, and these are all high temperature, high pressure, and we are much more safety concerned because any leak is a radioactive leak going out. So these materials should have a much more stringent property requirement than in the material which we use in other industries. So we have to get high quality material. You have to ensure their properties not only at room temperature, not only at operating temperature. Their property should not degrade even after 20, 30, 40 years in a reactor environment. And all those information we need to get. And then we also we need to, another important thing, we need to also test material, irradiated material also. See, we now put in a reactor, we come put 2-3 years or 5-6 years reactor, some material was inside the reactor, it has come out. Then we may to test how many more years we can use the reactor. Then we may to test whether how much property deterioration has taken place. And this entire thing has to be done in a radioactively shielded environment, a very big task. So many tasks are very, very unique material metallurgical tasks are there in a atomic energy environment. And another thing, some of the materials we have to generate by ourselves. See, zirconium alloys, it is not used in any other place. It is used in nuclear industry because zirconium does not absorb a neutron. So most of our reactor concept, we use zirconium as a material in which fuel this uranium oxide or plutonium oxides are put. So the uranium, the zirconium is used. So zirconium metals have to be there. So entire metallurgy of zirconium from ore to melting and producing and putting in the form of tube, and then entire new material to study. But for nuclear industry, nobody would have studied zirconium metallurgy.
Okay. Thank you, sir. Sir, another question is coming up. A general question. Can you please tell us the opportunities for material science in India?
Material science in
India.
India. See, if you look at it, this conventional field, material science, it is maybe, I would say it is more or less stagnant type of things. See, we have many more steel plants coming up, and there's when I was a student, we had only SAIL and Tata Steel making steel. Today, we have the major steel manufacturer in India is Jindal Stainless Steel, Jindal Steel Works, which has come up much later. So we have many steel plants where we have we can have this material. Another thing is we have another important aspect. We have to be very specifically look for it, because they will not advertise. From outside it may not appear that there is a big opportunity, but there are many big R&D institutes, especially R&D institute of multinational companies set up in the country. See, like General Electric has a very big R&D lab in Bangalore, and they actually take many metallurgists. And we have academic institutions, certainly it is there, and we have other, and there are a lot of fabrication industry, like industry like L&T. There are many things. People are there, and other. We also have BHEL Trichy, where there is a strong metallurgy, like where fabrication is there. And one more thing is, more and more people are getting aware. If you want a good quality control system, a quality assurance system in the industry, we need a metallurgist. See, now for a very good experience, I can tell you. See, many people from, especially from Kerala and other parts of country, go to Gulf. Maybe they go with a diploma, or they BSc engineering, and they start working as a inspection agencies, and they actually come back to get additional qualification in welding, metallurgy in the country, so that they can become a welding inspectors, they're going to NGT inspectors, all those things. So all those opportunities are there, and it is coming up. And another, as I told you, as the awareness of quality increases, there will be more and more opportunities for material scientists, and a big opportunity and at present in R&D level is on nanomaterials and these new materials. And because many nanomaterials, everybody is exploring, and when it comes to nanomaterial, the boundary between metallurgy and material science is disappearing. It's all together, and they use high-end equipment and facilities, and now they are making many of the nanomaterials are coming into the product form. Now we do not, as I told you, graphene, what is the opportunity to offer, we still do not know. But all those things are going to give more and more opportunity to the metallurgists in the country.
Sir, can we have two more questions?
Yes.
Sir, one is a technical question. Does magnetic property of the material is only reason for the formation of allotropes?
No. Allotrope is, it is nothing to do with the magnetic property. Different allotrope has different magnetic property. See, allotrope iron, which austenite, has one particular magnetic property. That ferrite, ferrite has a different magnetic property. So it is the crystallographic structure is having different. See, now if you look at next to iron in the periodic table is cobalt. That is also a ferromagnetic material. It also has transition from not from ferrite to BCC to FCC. It has a transition from hexagonal structure to FCC structure. But but both are close packed. So there won't be much difference as we have in this. So that they are independent. The crystal structure and they are independent.
Okay, sir. Sir, one last question. It's actually an inquiry from one of the participants. Why don't the Uranium Corporation of India, UCIL, hire metallurgists? I don't know why such
No,
query
no.
has.
I think there will be metallurgists there also, but see, basically, they will require process engineers, basically chemical engineers, because it is a chemical process involved. Because from uranium, very lean ore of uranium, that is uranium content will be very less, and from there you want to make in the form of a uranium oxide or something, and they don't make uranium metal. See, uranium as a metal we don't use much. Mainly we use as an oxide only. So it is truly not, in a sense, not a metal extraction. So it is basically a mineral extraction process. And so there's most of our requirement is with respect to running a process plant. So what they will require is a chemical engineers more, and then mechanical engineers for the process sheet optimization, and all the plant running electrical engineers. But still they may have a unique, the few numbers of metallurgists they will have.
Thank you, sir. Sir, for all the other queries, we will take from the participants, and we will let you know so that we can have a discussion later. So, sir, one more last thing after explain. Can we call carbon as the universal element?
See, it is almost true. See, because if you look at it, carbon, you tell me where carbon is not there. It is a very important element.
Sir, the
See,
remaining.
so why so? This is where I also wonder why so. See, these are the things which we still don't, we may not, we can explain based on the science, but why they exist that way? It's a question we may to ask the creator.
Okay, sir. Sir, can we take one more question, or shall we?
Yes, no, we can take.
Sir, it's again BCC is stable at lower temperature, but in iron carbon diagram, delta ferrite, which is BCC, is stable between 1410 to 1539 degrees Celsius.
Manu, can you go to the slides
Yes, sir.
where that magnetic property I told? No, that slide you show, if you show, it will be clear.
Sir, is it visible?
The next slide. Yes, next slide. Next slide.
Yes, sir.
So here you see in the middle graph, the graph in the right side. See that the two curves are crossing. So in the range in which the line corresponding to gamma is below, that is line corresponding to alpha. In that temperature range only gamma is stable. Below that it is alpha stable. Above that it's again alpha is stable.
Okay, sir.
I hope it explain you.
Yes, sir.
Did it answer the question?
Sir, I think the participant would have. He would have got the answer. Sir, another final. With this, we'll wind up, sir. Sir, one last question. Are there any natural alloys present?
See, it's a question. See, first of all, there are very few metals present. Actually, gold is one. Almost pure gold we can get. But most of the alloys are oxide in the nature. So we have to extract them. So what will naturally what is present is a mixture of compounds of or ores or minerals of different metals. See, in fact, if you make steel or if you make iron, there will always be some manganese, because iron ore contains some sort of manganese ore also. So as I told you, nickel and copper. When you have a nickel, when you extract nickel, some copper will come. Similarly, another important thing is nickel and cobalt is like that. If you extract copper, try to extract nickel, some cobalt will automatically come. And it is the same case with the zirconium. Zirconium and hafnium are together. So, in fact, there is a very interesting thing about zirconium and hafnium. They are chemically they are very close, but neutron cross section, the neutron absorption capability wise, they are widely apart. So chemically they are close, they will exist together. So when you extract zirconium, hafnium also will come. But zirconium with the hafnium we cannot put in reactor because it will hafnium will take all the neutrons, even small quantities. So we have to separate hafnium from this. So actually it is like this.
Okay, sir. Sir, the remaining questions we will take up in the future. We will collect the questions from the participants and we will let you know.
Yes, thank you.
So now over to Mebindi Kurula.
And thank you, sir, for the very informative talk. Now I request Vishnu Kesri,
Okay, thank you, Mevin sir. So good evening, one and all. So on behalf of the Department of Metallurgical and Materials Engineering, Amalchoudi College of Engineering, I would like to extend our sincere thanks to Dr. Shaju K. Albert, who is a Group Director of MME Group, IGCAR Kalpakkam, for accepting our invitation to take this session. So it was indeed a very interesting and enlightening talk for all the participants, not just the school students, but also for all the other graduate students as well as the faculties and the research scholars who are present for this session. We are also expecting your cooperation for our future endeavors also. So our heartfelt thanks to all the members for the active participation. So before we are winding up today's session, I would like to remind you about our next session as a part of this national webinar series. So I will show you the details of the next session. So I hope it is visible to all. So the next session will be on July 25th, which is opportunities awaiting a materials engineers in welding sector and quality inspections. So you can see the details which I have shared on the screen. So this will be our next talk as a part of this webinar series. So all the existing participants can continue to attend this session with the details that has been shared to you. And for any new participants, they can again register for this session. Now
So
the
once
current
again,
session.
reminding all the participants to fill out the feedback form shared in the chat box so that the participation certificates can be sent to your mail at the earliest. So before leaving, I request all the participants to kindly share the feedback with us. So over to Vishnu sir.
So all the participants can see the session which has been taken today in our YouTube channel. So you can see our YouTube channel, the Department of MME. So you can see the video of this session will be uploaded here, and you can see the session in the future also by checking this particular channel. Also further details you can see on our department Facebook page. So this is our Facebook page. It's the Department of Metallurgical and Materials Engineering, AJC. So all the information regarding this webinar series will be put over here. So you can look for it here also. So thank you.
So once again, we thank all the participants and especially Shaju sir for giving this talk and making this opportunity so that to bring out enthusiasm and interest in the participants and as well as students, comprising of students, faculties, research scholars, everybody across India in generating enthusiasm as well as their interest towards metallurgical and materials engineering and also to make them think of new opportunities as well as new chances that brings the scientist or the researcher in them. So I thank you, Shaju sir, once again for providing us this opportunity.
On my personal behalf, I also thank Manu and Amalchoudi College of Engineering for giving me this opportunity to share because for me metallurgy is a passion. So I don't mind sharing the passion with others. Thank you so much.
Thank you, sir.
Thank you so much.
Thank you so much. Okay, sir. So we hope all the participants have enjoyed the session, and we are sure we will meet again on next Saturday evening for the next session in this webinar series. So we hope everybody is safe during this Corona period, and we hope to see you everyone during next Saturday. So till then, we all are signing off from here till next Saturday, till we meet you, all of you again. So have a nice weekend. So goodbye.
Goodbye.